Hey there, welcome back to Pescara Labs. Today we're going to explore something that makes networking in the cloud much simpler. But before we dive in, let me set the stage for you. Imagine you're running a growing company. You have multiple offices, each with its own network. Your teams are building apps, storing data, and accessing resources across different locations. Now, connecting all these networks one by one is possible, but it quickly becomes messy, complicated, and hard to manage. What if I told you there's a way to simplify all of this? A single hub that lets all your networks talk to each other securely and efficiently. That's exactly what we're going to learn today with AWS Transit Gateway. By the end of this tutorial, you'll see how to connect multiple VPCs in minutes, test the connections, and understand why cloud networking doesn't have to be complicated. So grab your coffee and let's jump in. All right, now that we understand why connecting multiple networks can get tricky, let's talk about AWS Transit Gateway, the solution to simplify all that complexity. Think of AWS Transit Gateway as a central hub, like the main station in a busy train network. Instead of building separate tracks between every station, all trains can go through the central hub. Similarly, Transit Gateway connects multiple VPCs in one place, making communication seamless and manageable. It doesn't just simplify network management, it's also highly scalable and designed for high performance. So whether you have a few VPCs or dozens, it can handle the traffic efficiently. And it's not limited to the cloud. Transit Gateway also supports hybrid architectures, letting your on-premises networks connect securely to your cloud environment. Best of all, it gives you centralized control over routing, so you don't have to manage dozens of route tables across multiple VPCs. Everything comes together in one place. In short, AWS Transit Gateway is your one-stop hub for efficient, scalable, and manageable cloud networking. Now that we know what a transit gateway is, you might be wondering, how is it different from VPC peering? Let's break it down. VPC peering is like a direct road between two houses. It's simple and works well if you only need to connect a couple of VPCs. But if you have many VPCs, suddenly you need dozens of roads, and managing all those connections can get messy fast. Transit Gateway, on the other hand, is more like a central hub in a city. All your VPCs and even your on-premises networks connect to this hub. That means you can manage thousands of VPCs from a single point, and the network stays organized and scalable. With VPC peering, each connection has its own routing, so managing routes can get complicated. Transit Gateway centralizes routing, making it easier to control your network traffic. When it comes to hybrid cloud setups, VPC peering is limited. You'd need separate VPNs for each VPC. Transit Gateway makes it simple, supporting both VPN and Direct Connect to link your on-premises networks. And while VPC peering might be cheaper for small setups, Transit Gateway simplifies large-scale architectures, which can save time and reduce complexity in the long run. In short, VPC peering is great for small, simple connections, but Transit Gateway is the go-to solution when your cloud network is growing and you want centralized, scalable, and manageable connectivity. Now that we know what a transit gateway is and why it's useful, let's get hands-on and see it in action. Here's the workflow we'll follow step by step. Step 1. Create two VPCs. Think of these as two isolated neighborhoods in the cloud. Each has its own network and resources, but right now, they can't talk to each other. Step 2. Create subnets and route tables. Next, we'll create subnets inside each VPC. Subnets are like the streets within each neighborhood, and route tables act like maps, guiding traffic to the right destination. Step 3. Create VPC endpoints. Optional. We can set up VPC endpoints These allow your instances to securely access AWS services without traversing the public internet, like having a private tunnel to your favorite services. Step 4. Launch 2 EC2 instances. Now, we'll launch one EC2 instance in each VPC. These will be our test machines to check connectivity and make sure our setup is working correctly. Step 5. Test initial connectivity. Before connecting the VPCs, we'll test connectivity between the two instances. Since the VPCs are isolated at this point, the ping will fail, and that's exactly what we expect. Step 6. Create Transit Gateway. Here comes the key part. We create a transit gateway. Think of it as a central hub that will connect our two isolated VPCs into a single manageable network. Step 7. Attach both VPCs to the transit gateway. This is like building the roads from each neighborhood to the central hub, enabling communication between them. Step 8. Update route tables. We then update the route tables in each VPC to route traffic through the transit gateway. This ensures that all network traffic knows the correct path to reach the other VPC. Step 9. Test connectivity once more. This time, the ping between the two instances should succeed, showing that our transit gateway is working perfectly and our VPCs are now connected. And that's the full workflow. With just these steps, you've successfully connected multiple VPCs using a transit gateway, making cloud networking simpler, scalable, and centralized.
Step 1. Let's create our two VPCs. This is where our cloud networks will live. Think of them as two separate neighborhoods, each with its own address space. First, go to the VPC console and click on Your VPCs, then select Create VPC. For the first VPC, we'll give it a name, Demo VPC1, and set the CIDR block to 10.1.0.0/16. This defines the IP range for our first network. Next, create the second VPC. Name it Demo VPC2 and set the CIDR block to 10.2.0.0/16. This ensures the two networks don't overlap and can communicate properly later through our transit gateway. Finally, click Create VPC, and just like that, we have two separate VPCs ready for the next steps in our tutorial. Step 2. Let's break our VPCs into smaller sections by creating subnets and set up route tables to guide the traffic. Head over to the VPC console, then go to Subnets and click Create Subnet. For our first VPC, Demo VPC1, create a subnet with the CIDR block 10.1.1.0/24. This subnet will act like a street inside our first neighborhood. For the second VPC, Demo VPC2, create a subnet with the CIDR block 10.2.2.0/24. Another street, but in a separate neighborhood. Next, we need route tables for each VPC. These act like traffic maps, telling network traffic where to go. Create a route table for Demo VPC1 and associate it with its subnet,
Then do the same for demo VPC2 and its subnet. Now, each subnet has its own route table, and traffic within each VPC knows exactly where to flow. With this setup, our networks are ready for instances and later for the Transit Gateway connection. Step 3 is optional but highly recommended: creating VPC endpoints. These endpoints allow your instances to connect to AWS services privately without going over the public internet, like having a private tunnel straight to your services. In the VPC console, go to Endpoints and click Create Endpoint. Choose the service category EC2 Instance Connect Endpoint. Select Demo-VPC-1 as the VPC and choose the subnet Demo-Subnet-1. Then click Create Endpoint. Repeat the same process for Demo-VPC-2, selecting its corresponding subnet. Once both endpoints are created, wait until their status shows Available. This means they're ready to use. With these endpoints in place, our EC2 instances will have a secure, private path to connect to AWS services, making our network setup even safer and more efficient. Step 4. Let's launch our EC2 instances. These will be our test machines to check connectivity between the VPCs. Head over to the EC2 console, go to Instances, and click Launch Instance. For the first instance, select Demo VPC1 and the subnet Demo Subnet 1. Make sure to configure the security group to allow ICMP for ping and SSH so we can connect remotely. Next, create the second instance in Demo VPC2 using Demo Subnet 2 and a similar security group that allows ICMP and SSH. Once both instances are launched, wait until their status shows running. These instances will help us test network connectivity before and after connecting the VPCs through the Transit Gateway.
Step 5. Let's test the initial connectivity between our two EC2 instances. First, connect to EC2 Instance 1 using EC2 Instance Connect. Try pinging the private IP of EC2 Instance 2. Next, connect to EC2 Instance 2 and ping the private IP of EC2 Instance 1. And here's what we expect. There's no reply. That's because the VPCs are still completely isolated from each other. Each EC2 instance lives in its own private network, and right now, there's no route for traffic to travel between them. This isolation is normal, and in fact, it's exactly what we want to see at this stage. It proves that each VPC is functioning independently, which is the starting point for our transit gateway setup. Think of it like two houses on separate streets, each with its own locked gate and no connecting road. If someone in one house wants to visit the other, there's currently no way to do it. The houses are safe and private, but they also can't communicate. That's okay, because our next step will change everything. We're about to build the road, the bridge, and the central hub that allows these two isolated networks to talk to each other seamlessly, securely, and efficiently. By the end of this tutorial, those two houses, or VPCs, will be connected through a single, well-managed network hub, making cloud networking much easier to handle.
Step 6. Now comes the exciting part, creating our transit gateway. This is the central hub that will connect our previously isolated VPCs, allowing them to communicate seamlessly. Head over to the VPC console, then navigate to Transit Gateways and click Create Transit Gateway. Give it a name, let's call it Demo TGW1. For this tutorial, we'll leave all other settings at their defaults, which are sufficient for a basic setup. Once you click Create Transit Gateway, AWS will start provisioning it. Think of this as building the central station in a railway network, the hub where all your network traffic will converge and be efficiently routed between your VPCs. After a few moments, your transit gateway will be ready, and we'll be able to attach our VPCs to it in the next step.
Step 7. Now that we have our transit gateway, it's time to attach our VPCs. This is where the magic happens, connecting our previously isolated networks to the central hub. In the VPC console, go to Transit Gateway Attachments and click Create Attachment. Select our transit gateway, Demo TGW1, and then choose Demo VPC1.
Make sure to select the subnet Demo Subnet 1 so that traffic from this subnet knows to route through the hub. Repeat the same process for Demo VPC-2, selecting Demo Subnet 2. Once both attachments are created, wait until their status shows available. This means both VPCs are now successfully connected to the Transit Gateway. Think of it like building two roads from each neighborhood straight into the central station. Now, both VPCs can start communicating through the hub, but we still need to update the route tables to complete the connection.
Step 8. Now that both VPCs are attached to the Transit Gateway, we need to update the route tables so the traffic knows exactly where to go. For Demo VPC-1, open its route table and add a new route. Set the destination to 10.2.0.0/16, which is the sidecar block of our second VPC, and set the target to the Transit Gateway. This tells VPC-1 that any traffic meant for VPC-2 should go through the hub. Next, for Demo VPC-2, do the same. Add a route with the destination 10.1.0.0/16, which is VPC-1's sidecar block, and again, set the target to the Transit Gateway. Now both VPCs know how to reach each other through the central hub. Think of this like updating the street maps in each neighborhood, adding clear directions so that traffic can flow smoothly through the central station. With the route tables updated, our VPCs are ready to communicate.
Step 9. The moment of truth. Let's test the connectivity between our EC2 instances now that the Transit Gateway is set up.
Go back to the EC2 console and connect to EC2 instance 1. Try pinging the private IP of EC2 instance 2. Then connect to EC2 instance 2 and ping the private IP of EC2 instance 1. This time, you should see a successful reply. The two instances can now communicate perfectly through the Transit Gateway. It's like our two previously isolated houses are now connected by a smooth, well-maintained road leading through the central hub. Messages can flow freely, securely, and efficiently. This proves that the Transit Gateway is working exactly as intended, connecting multiple VPCs with a single, manageable hub. Congratulations! You successfully set up a Transit Gateway and connected your VPCs.
And that brings us to the end of today's tutorial. Let's quickly summarize what we've done. We started by creating two separate VPCs, added subnets and route tables, and optionally set up VPC endpoints for secure access. Then, we launched EC2 instances in each VPC and tested initial connectivity, which, as expected, didn't work because the networks were isolated. Next, we created a transit gateway, attached both VPCs to it, updated the route tables, and tested connectivity again. This time, our EC2 instances could communicate perfectly, proving that the Transit Gateway successfully connected our networks in a scalable, centralized way. In conclusion, AWS Transit Gateway is a powerful tool that simplifies cloud networking, centralizes routing, supports hybrid environments, and makes it easy to scale your network as your cloud infrastructure grows. If you found this tutorial helpful, don't forget to like, comment, and subscribe to Bagaskara Labs. Your support helps us create more hands-on tutorials to make learning cloud technologies easier and more fun. Thank you for watching, and I'll see you in the next video here at Bagaskara Labs.